Hello everyone, welcome to this applied remote sensing training on assessing extreme weather statistics using NASA Earth Exchange Global Daily Downscaled projections for Coupled Model Intercomparison Project Phase 6 or NEX-GDDP-CMIP6. My name is Amita Mehta from ARSET and we have a guest speaker today, Dr. Thrasher from Climate Analytics Group. I will be introducing her shortly. Part 1 today is going to focus on NEX-GDDP-CMIP6 overview and then data access and application using Google Earth Engine. We'll start with a brief introduction to Applied Remote Sensing Training Program or ARSET. ARSET provides accessible, relevant and cost-free training on remote sensing satellites, sensors, methods and tools. Trainings include a variety of applications of satellite data and are tailored to audiences with a variety of experience levels. ARSET trainings focus on these thematic areas listed here on the right hand side. ARSET trainings are online and there are in-person trainings offered as well. Most ARSET trainings are live and instructor-led, but there are a few asynchronous and self-paced trainings available through ARSET website. They're cost-free, they're bilingual and sometimes multilingual. Bilingual because most of our trainings are translated in Spanish and some are even offered in Spanish. Occasionally, they are offered in French. ARSET only uses open source software and data and they accommodate differing levels of expertise. We'll start today's session with a brief background about extreme weather events. So why study extreme events? According to World Meteorological Organization, the frequency and intensity of extreme weather events, including heat and cold waves, heavy precipitation and droughts, and wildfires, have increased fivefold in last 50 years. The latest WMO European State of the Climate 2024 report shows spiraling effects of weather and climate impacts, and that is shown in this animation. What this shows is monthly mean temperature differences for all months for multiple years, starting from 1860 all the way to 2023. And these temperature differences are taken with respect to a baseline temperature of 1850 to 1900. And we see that as years progress, the temperature differences are increasing. And we are currently here in 2023. So this is what this report means: spiraling effects of weather and climate impacts. And as a result, extreme weather continues to bring devastating consequences globally and has significant economic and social upheavals. So to understand societal impacts of these extreme weather events, it is important to study them. Now, Earth observations from NASA allow monitoring of extreme events from the last 20 plus years to near real time, and you can look at these websites to get more information how satellite data have been used to monitor extreme events from the past and in near real time. However, for developing regional adaptation and mitigation strategies, it is crucial to assess how extreme events will unfold over the coming decades. So we want to know the future of these extreme events, and for that we have global climate models. Globally, there are more than 50 modeling institutions working on developing Earth System Models or ECMs, and currently more than 100 ECMs are available. Leading modeling groups have coordinated simulations of climate change scenarios within Coupled Model Intercomparison Project or CMIP, which is currently in Phase 6. As we will see later in this session, there are more than 30 models participating in CMIP6, and the CMIP6 global climate models, they are constantly improving and they provide predictions and projections of extreme events. However, the typical spatial resolution of GCMs is lower than 1 degree latitude and longitude, and therefore for regional applications, NASA Earth Exchange Global Daily Downscale projections provide global, high-resolution, bias-corrected projections of daily weather parameters from CMIP6 GCMs at quarter-degree resolutions. So it's improved high resolution in its bias-corrected data that we are going to focus on in this training. Here's an example of NEX-GDDP climate evolution projection. What this shows is spatial pattern of years exceeding the 2-degree warming with respect to the baseline period 1950 to 1979. The 15-year moving average of the ensemble median of near surface air temperature from 35 CMIP6 models are considered here, and the scenario considered is SSP 585, which is the highest emission or highest radiative forcing scenario. And what we see here is that this is the timeline and this is the pattern. In northern hemisphere at higher latitudes already temperature has exceeded 2 degrees Celsius, and as we go to other parts of the world, between now and 2050, most of these parts will exceed 2 degrees Celsius warming. There are some parts which will catch up later after 2050. But what we want to know is that as this warming is occurring, how do we see change in extreme weather conditions? And so the training learning objectives based on that are given here, that by the end of this training, we will be able to identify available daily high-resolution geophysical parameters from NEX-GDDP-CMIP6 to assess extreme weather statistics at a regional scale. There will be 3 ways how we can access this NEX-GDDP-CMIP6 data and analyze. So that what we will see is that access daily temperature and precipitation data for a region of interest to calculate and analyze weather statistics using NEX-GDDP-CMIP6 data in Google Earth Engine. Visualize maps of extreme weather statistics for a region of interest using NEX-GDDP dashboard. Customize provided Python Jupyter Notebook scripts to calculate extreme weather statistics for a region of interest. And finally, assess projected statistics of extreme heat and cold wave events and excess and deficit precipitation events from these models at regional scale during the 21st century to evaluate risk for a region of interest. There are several prerequisites for this training. These are past ARSET trainings which are highly recommended to follow this current training better. Fundamentals of remote sensing, then this drought monitoring, prediction and projection training has a session on GDDP data. Also, there are trainings on climate change projections and climate change monitoring and impacts. So these trainings are highly recommended. More importantly, there will be hands-on exercises and homework in this training, and for that you need to create a user account on Google Earth Engine and register to a non-commercial cloud project. So here is the link, and then get started and follow the steps so you can create a cloud project on Google Earth Engine, and you will be provided Google Earth Engine code so you can execute and work with GDDP data. Then more importantly, there are these 2 sites. Before the next session, you should be able to access these sites so that you can work with the data. There's a dashboard that you will be working with to look at visualization of GDDP extreme weather statistics data, and then you will be using Python Jupyter Notebook code. So for that, please make sure that you can access these sites. So these are the prerequisites. Overall outline is that there will be 2 parts. Today we will focus on overview of NEX-GDDP-CMIP6 and data access and application using Google Earth Engine. And the next session will be on extreme event statistics during 21st century using NEX-GDDP data, and this will be looking at GDDP dashboard as well as learning to use Python Jupyter Notebook code for accessing data. There will be one homework that will be posted on 17th of September. That's the last day of the training, and it will be due after a month on 17th of October. So this homework will include some hands-on exercises from today as well as from 17th, and you will be answering a number of questions based on that. A certificate of completion will be awarded to those who attend all live sessions and complete the homework assignment before the given due date. So we start with part 1, NEX-GDDP-CMIP6 overview, data access and application using Google Earth Engine. Our objectives for today are that by the end of part 1, you'll be able to identify NEX-GDDP-CMIP6 data characteristics and recognize how to access and analyze GDDP data for applications using GEE. Outline for today is that we'll start with an overview of NEX-GDDP-CMIP6 project and data, and this will be by Dr. Thrasher. After that, we will have a demonstration in analysis of extreme event statistics from GDDP data using GEE. We'll have a case study focusing on Nebraska, the state in the United States, and we will look at seasonal extreme cold and hot event frequencies and wet and dry event frequencies using GEE. After the demonstration, there will be some time for hands-on exercise in which you will be using the same script. Just repeat the calculations so that you can use your Google Earth Engine account, and there will be a homework based on this exercise. How to ask questions? Just a note, please put your questions in the questions box and we will address them at the end of the webinar. Feel free to enter your questions as we go, and we will try to get to all the questions during the question and answer session after the webinar. The remainder of the questions will be answered in the question and answer document, which will be posted to the training website about a week after the training. With that, I want to introduce our trainer for today, Dr. Thrasher. Dr. Thrasher is a co-founder and climate scientist at Climate Analytics Group. Her areas of expertise are climate modeling and methods, including statistical and dynamical downscaling, as well as scientific programming and data analysis. Her employment background includes Oracle, NASA Ames, and various Silicon Valley startups. She holds a BS from the California Institute of Technology and a PhD in Earth Science from the University of California, Santa Cruz. Dr. Thrasher is awarded NASA Exceptional Public Achievement Medal this year. So we're fortunate to have Dr. Thrasher talking about NEX-GDDP-CMIP6 project. And with that, I hand this over to Dr. Thrasher. Bridget?
Thanks, Amita, for the introduction, and hello, everyone. Thank you for joining us today. My name is Bridget Thrasher, and I am the creator of the NEX-GDDP-CMIP6 archive, as well as other NEX downscaled data products. So before we get into the details of downscaling and GDDP, I would like to just take a moment to tell you about NEX, and that stands for NASA Earth Exchange. And NEX is a platform for collaborative computing and data analysis. The purpose of NEX is to improve the availability of NASA's Earth science data through this centralized environment. So, and access to NEX is available to researchers who are supported by the ROSES program and various flight projects. In addition to ROSES and the flight projects, NEX also supports a variety of NASA programs, such as the MEASURES program, the Carbon Monitoring Systems program, the Global Ecosystem Dynamics Investigation program, the National Climate Assessment, Geostationary Research, Advanced Information Systems Technology program, Applied Sciences program, and visualization for the Earth Observing System Data Information System. Okay, so now that you understand what NEX is, let's take a look at downscaling in general. So what is downscaling? Well, downscaling is a process that transforms low-resolution model data into higher resolution information. This is with the goal of making that information more suitable for regional and local scale impact and adaptation studies. And there are two types of downscaling methods. One is dynamical downscaling, and this involves using a regional climate model over a specific geographic area, with the boundaries of that region being driven by the low resolution global model output. The other type of downscaling method is statistical downscaling, and this method uses statistical relationships between large scale and local scale climate data to perform that transformation to the global model output. So let's look a little further into these two types of methods. So what is dynamical downscaling? Well, as I just mentioned, this method uses a regional climate model driven at the boundaries by global climate model output. The advantages to this type of method are, one, it does not rely on the stationarity assumption, meaning that instead of assuming that the properties of regional and local climate will remain constant over time, those characteristics are allowed to evolve with the physics that underlie the regional model. And two, the regional model does not require any inputs other than the GCM model output, the global climate model output, at its boundaries. However, as with all models, there are disadvantages to this method as well. First, it's computationally very expensive, especially as you increase the target resolution. So this makes creating a large ensemble of downscaling output from many GCMs a challenge. Second, the regional model will automatically inherit the bias and uncertainty that's contained in the GCM output. And this is actually in addition to the bias and uncertainty that's associated with the regional model itself. And lastly, the regional models are limited to recreating the large-scale atmospheric patterns of the driving GCM. So for example, the regional model won't adjust the location of the jet stream as is determined by the global model. And what is statistical downscaling? Again, as I stated earlier, statistical downscaling uses the statistical relationships between large-scale and local-scale climate data to transform the global model output. Again, because no method or model is perfect, it has its advantages along with disadvantages. So the first advantage is that the output from the global models are adjusted to alleviate their systematic bias. Second, the spatial coverage and resolution are determined by the reference observational data as opposed to being determined by computational resources. Therefore, these methods are much less computationally expensive and can therefore be easily used to create large ensembles of downscaled output. The disadvantages to statistical downscaling methods are that they do rely on the stationarity assumption so that the large-scale characteristics of the reference data are assumed to be constant over the time period being downscaled. Second, your downscaled variables are limited to those that are available in the reference data set. Okay, now let's move on to the details of NEX-GDDP-CMIP6, which I will just refer to as GDDP from here on out. GDDP stands for Global Downscaled Daily Projections, and this is an ensemble of statistically downscaled output of models from Phase 6 of the Climate Model Intercomparison Project, otherwise known as CMIP6. And CMIP is a project of the World Climate Research Program that provides climate projections from modeling centers around the world to understand past, present, and future climate changes. So the GDDP products have a daily temporal resolution and span the globe at a 1/4 degree horizontal resolution. The archive contains downscaled output from 35 different CMIP6 models and 5 different CMIP experiments. The historical experiment spans 1950 to 2014, while the forward-looking experiments span 2015 to 2100. And these experiments of future climate comprise 4 different pathways, as shown here. So SSP1 is considered a sustainability scenario that ends with 2.5 watts per square meter forcing by the end of 2100. SSP2 is a middle of the road scenario with increased carbon forcing followed by mitigation. SSP3 is a regional rivalry between different parts of the globe. SSP5 is a full fossil fuel development scenario, also often called business as usual scenario. And just to let you know, GDDP, earlier this year, we released version 2 of the archive. So if you're going to use it, make sure you're using the version 2.0 files. And GDDP contains 9 different climate variables as listed here. Relative humidity, specific humidity, precipitation flux, surface downwelling long wave radiation, surface downwelling short wave radiation, near surface average wind speed, average daily temperature, maximum daily temperature, minimum daily temperature. And these 9 were processed for each of the CMIP experiments as available from each global model. The GDDP files have the following properties. So each individual file contains 1 year's worth of data for a single variable. Please note that not all the GCMs use the same calendar, so the number of days within a file will depend on the original calendar system used by the model. All files are in a compressed NetCDF classic format and follow the CF 1.7 metadata conventions. The files average around 250 megabytes each for a combined data volume of about 30 terabytes. And lastly, the archive is made available through a Creative Commons Zero license, which means that it is entirely within the public domain and can therefore be used for any purpose. Okay, so now that I've given you the overall details of GDDP, let's move on to look at how it was actually created. So as discussed, GDDP is a statistically downscaled product. In particular, a method known as BCSD, which stands for Bias Correction Spatial Disaggregation, was used to process the global climate models. This method was actually first developed for use with early iterations of CMIP output, which way back then were only available as monthly aggregates. So this method was later modified to use with data at a daily time step. Beyond the global model output, the BCSD method requires a reference data set. These are typically gridded observations or a reanalysis product. For GDDP, we used the Princeton Global Forcing Data Set, which is also known as the Global Meteorological Forcing Data Set, or GMFD. Just as a side note, because the forcing data required some adjustments before use with the BCSD algorithms, I made the processed version available through a Google Drive that is linked here. In order to calculate the statistics and adjust the GCM biases, the reference dataset time series must overlap with the output from the CMIP historical experiment. So for GDDP, a reference period of 1960 to 2014 was used. So with both of these ingredients, the GCM output and the reference data set, we can apply the two-step BCSD algorithm, which consists of a quantile mapping scheme for bias correction, followed by a spatial disaggregation of residual fields. All right, so let's look at the details of the first step, which is an adjustment of the biases of the raw GCM output. And why do we want to do this in the first place? Well, as you see here in this diagram, all GCMs have inherent biases, such that while they likely have reasonable large-scale properties, the exact values can be far from those seen in the observational record. We can therefore use this comparison to adjust the GCM results to be closer to those that we expect. So BCSD uses a quantile mapping scheme for adjusting that bias. We're going to walk through an example of how that works. So in this example, let's assume that we are adjusting the daily maximum temperature on February 14 or Julian day 45 of some year that's been output by our GCM. The daily BCSD method uses a plus or minus 15-day moving window to form a sample from which to calculate the bias corrected value. And this allows us to have a large sample size while also ensuring that the variables are all being adjusted from values that are taken from the same time of year. So in this example that we're stepping through, our sampling window spans Julian days 30 to 60. Now that we have the extent of our sampling window, we need to gather all the values for all the days within that window for each year in the reference period. So in the case of GDDP, this reference period was 1960 to 2014, which yields approximately 1,700 data points when taking the full sampling window into account. So we gather these values from both the output from the CMIP historical experiment for the GCM being downscaled, and from the reference data set, which has been aggregated beforehand to the native GCM horizontal grid. Next, we take those two pools of values and create cumulative distribution functions, or CDFs, for each one. And those are shown here in the bottom panel. The green line is the GCM model output, and the red line would be the observation of the reference data set output. All right, so now that we have the two CDFs in place, we use them to adjust the GCM bias for the value on the day of interest. See here, Julian day 45. So here our GCM value in this example is 29 degrees Celsius. And based on the CDF created from the GCM values in green, this equates to a quantile of 0.78. Next, we use the CDF from the reference data set in red to find the temperature value that lies at that 0.78 quantile. So in this example, that's a value of 32.5 degrees Celsius. So we replace the original GCM value of 29 degrees with the reference data set value of 32.5 degrees. We then repeat this process for every day and every grid cell within our region and time span to be downscaled. This results in bias-corrected GCM output that is now more closely correlated with the reference data set. And now we have concluded the first step in the BCSD downscaling process, from a low-resolution native GCM output to a bias-adjusted version at that same resolution. So the bias correction step takes place on the low resolution grid that's native to the GCM being downscaled. So now we must take those low resolution bias corrected fields and disaggregate them to the target high resolution grid of our reference data set, while at the same time preserving the daily climatology in the process. So first, we need to calculate the daily climatology of the reference data set at its original horizontal resolution. In this case, it's at a 1/4 degree resolution. Next, we aggregate that high resolution climatology to the native grid of the GCM we are downscaling. And that low resolution climatology is then removed from the bias corrected fields we created in the first step, BCSD, to create these residuals. And this is done in an additive way for temperature and a multiplicative way for the finite variables, since they are bounded by 0. The residual fields that are left over are then disaggregated through bilinear interpolation to the target high resolution grid native to the reference data set. And then lastly, that high-resolution climatology that we created up in step 2A is returned to the disaggregated residual, again, additively for temperature and multiplicatively for the other variables. And we have now used the daily BCSD method to statistically downscale output from a relatively low resolution global climate model. And if you would like to see all the details, you can find the code used to produce GDDP on GitHub at the link provided here. All right, so because our goal is to make the NEX products available to anyone who wants to use them, we have made GDDP available through a number of different outlets. The authoritative source for GDP will always be through the data catalog at the NASA Center for Climate Simulation, NCCS. The link is provided at the bottom. However, for those who work in a cloud environment, you can also access GDDP on Amazon Web Services through their registry of open data, and these are free to access, again, at the link provided. Lastly, and what you will be learning about later, GDDP is also available through the Google Earth Engine. Okay, so let's recap what I've been discussing here today. The NASA Earth Exchange, or NEX, is a collaborative supercomputing and data analysis platform. It improves the availability of NASA's Earth science data from various missions and other sources. And NEX supports many programs throughout NASA. What is downscaling? So there are downscaling is a process that transforms coarse, low resolution climate model data into higher resolution data that are suitable for regional and local impact and adaptation studies. And there are two types of downscaling methods, both dynamical and statistical downscaling. NEX-GDDP-CMIP6 is an archive of statistically downscaled CMIP6 models, including daily output from the historical experiment from 1950 to 2014 and 4 future scenarios out to 2100. The archive was created using the daily BCSD downscaling method, which is composed of a bias correction process and a spatial disaggregation process. There are 9 variables included in GDDP as available from 35 global models. These include both relative and specific humidities, precipitation, both long wave and short wave downwelling surface radiation, near surface wind speed, and daily minimum, maximum, and average temperatures. Each GDDP file contains 1 year of data for a single variable, and the files can be accessed through NCCS, AWS, and Google Earth Engine. Thank you for your time and attention today, and I look forward to taking any questions shortly.
Thank you so much, Bridget, for your excellent presentation and such useful information about NEX-GDDP-CMIP6 and how to access the data. And that brings us to the last part of today's session, and that is going to be a demonstration of how to access GDDP data using Google Earth Engine. So what we're going to do is use Google Earth Engine to analyze extreme event statistics from GDDP and we'll use 2020 to 2100 data from GDDP using Google Earth Engine. For the demonstration, we've chosen a case study focusing on Nebraska in the USA. This is the state of Nebraska. Now, Nebraska's economy is heavily dependent on agriculture. It grows corn, soybean, and wheat, and cattle farming is also big in Nebraska. And because of the agricultural activity, it's quite sensitive to climate variability and change. And also it's part of the tornado alley in the US, this red area that you see here, where the most frequent number of tornadoes occur annually, and Nebraska is part of that. So that's why we're going to see how extreme event frequencies change over Nebraska during 2020 to 2100. In the demonstration, we will do GDDP data analysis for this period using Google Earth Engine JavaScripts. There are 4 different scripts, and you have access to these scripts through links provided on the training webpage. What we will do is first look at annual mean temperature and precipitation time series over this period and have maps of long-term mean temperature and precipitation over Nebraska. Then we will look at extreme cold events during winter seasons, extreme hot events during summer seasons, and look at extreme dry and wet events during summer seasons. So analyze temperature and precipitation over Nebraska. So I'm going to share my screen and show Google Earth Engine scripts here. So we'll start with Google Earth Engine main window. Here, this earthengine.google.com. You have to have a user account created with username and password to be able to get into Google Earth Engine, and also have to create or register a cloud project with GEE in order to run code on GEE or to use it. If you don't already have a cloud project registered, then you can go to this non-commercial option and follow the steps in there and create a cloud project, and then you will be able to run the scripts that we will share with you. On Google Earth Engine main window, you will see these 2 options. So let's start with datasets first. If you go to datasets, there is a search window, and you can search by either parameter name or dataset name. Here we already know we are looking for GDDP, NEX-GDDP data. So when you search with that string, all the options you will see here about the related to NEX-GDDP. The dataset that we are going to use is NEX-GDDP-CMIP6. Once you click on the data, it provides you information about that dataset. In this case, you can go to description, read about the data. Here you see Dr. Thrasher's paper referenced for GDDP. Dataset availability, so temporal coverage, temporal resolution, which is daily, and dataset provider. This is Earth Engine image collection, so EE image collection. This is the name. Every time you want to access this data in JavaScript code, this is the image collection you would start with. If you go to bands, you will see that names of these parameters, these 9 parameters that Bridget mentioned in her presentation, they are described here. This is near surface relative humidity, specific humidity, etc. Units are given here, minimum and maximum possible values, and pixel size, which is in meters. Another important thing to note is image properties. Here you will see by string all the CMIP6 models included in GDDP are listed here. For each of these models, data sets are available, and you can pick either one or many of these models by using this string. For our purpose, we are going to pick one model, and we are going to pick GIS E21G. This is the NASA climate model, so we will take that as an example today, but you can try different models as well. In addition to these models, one can pick a scenario for which all the models and parameters are available. First one is historical. These are retrospective model runs pre-2015, and these two are shared socioeconomic pathways or emission scenarios, SSP 245 and SSP 585. We'll talk more about it when we extract data. So you can pick a scenario, a model, and parameters that you want to use for your analysis. There are some additional image properties that you can review here. If you go back to the data description, you will see that along with the image collection, there is a snippet or a code snippet available. If you click on that in this arrow, then it takes you to the Google Earth Engine JavaScript screen here, and you will see 3 panels. Here is your repository with different code or scripts, information about Earth Engine documents and assets where you can upload your own data if you want to use in your script. And this panel can show results of your code, as well as there is a map panel here or map window here. Anything that you plot or maps that you make, they will be shown here. So as your results can be found here if you are plotting maps, or if there are any other analysis like time series, you will see in this window. You can start with your own code and build it, or in this case we already have a link for you, and you should have this link on the training page if you want to follow along. This is exercise annual temperature and precipitation. So this is what we'll start with, and then we will go to extremes analysis. So we'll start with the top 2 lines, this imports, and you will see that there's countries and sub-region, and there are 2 tables or feature collection. These are from Food and Agricultural Organization, FAO. These are Global Administrative Unit Layers, or GAUL. Level 0 is country level shapefiles, and level 1 have states or provinces within the country that you have selected. You have different shapefiles that you can import and then use in your code. So this is important to note, that you will have to import shapefile of the countries and region of your interest. This is the training description and training web page given here. This is the script name. This code is free and open, so you can save the script to your Google Earth Engine account and modify it and customize it the way you like it. But by using this code, you agree to cite the following reference in any publications derived from them, and that is NASA Applied Remote Sensing Training Program. So please acknowledge ARSET. There's a disclaimer that every effort is made to ensure the code is free of errors, but there is no warranty for the maps, and their features are either specially or temporally accurate or fit for a particular use. This code is provided without any warranty of any kind whatsoever, either express or implied. We've seen some of this information earlier already, that in Google Earth Engine, this data set has image collection name as NASA/GDDP-CMIP6. This is the collection you will always use to access this data in GEE. And as we saw earlier, in image collection bands and image properties, you will find options for choosing multiple atmospheric parameters, and also different CMIP6 models are available in there too. There are 2 shared socio-economic pathways for which data sets are available. First one is SSP 245, that is the middle pathway, and that is projected to have radiative forcing of 4.5 watts per meter square by 2100. And SSP 585 has radiative forcing of 8.5 watts per meter square by 2100. In this exercise, we will go through the following steps. we'll select one model from GDDP model ensemble. We'll select one SSP scenario, in this case SSP 245, the middle pathway. We'll select parameters, surface air temperature, the daily average temperature we'll pick, and precipitation. First, we'll collect daily data for these 3 years, 2020, 2050, and 2100. Clip the global data set to the area of interest. In this case, it will be Nebraska. And then find annual mean of near surface air temperature and precipitation for the 3 years for the area of interest. And we'll map these parameters and also their differences to see how patterns change in temperature and precipitation from 2020 to 2050 and 2020 to end of this century. Then we will have annual mean temperature and precipitation for each year from 2020 to 2100, and we'll make a time series to see variability and change in the time series, and we'll have this area averaged over Nebraska. We've already talked about FAO-GAUL dataset, and these are definitions of variables used in this code. I'm not going to read every line, but you can refer to these definitions or descriptions here. As we go through the calculations, I'll refer to some of these names or variables. So starting GDDP analysis here for Nebraska. This is assigning country and state from this level 1 administrative GAUL data. So here we are picking this feature collection and filtering it with the country of our interest and state of our interest and assigning it to my AOI. These two lines, they add this my AOI layer to this map. Here it focuses or it centers on my AOI, in this case Nebraska, with zoom factor 6, and colors the shapefile with blue color. And if you look at the map panel, once you run the script, this Nebraska will be highlighted here in blue. The shapefile will appear on the map. If you don't want to use country or state, but you have your own shapefile for a county or a watershed or even a city, there is a way to use that. That means upload your own area of interest. In that case, you will go to assets here and pick a shapefile from your computer with these extensions. And once uploaded in this tab, you can then if you go to assets, there are some examples here. You will see an arrow and then you can import that in your script. So this allows your own shapefile to be used instead of any predefined shapefiles for countries or state. So that also is a possibility. Okay. Now we're going to start with GDDP analysis. We define a variable data set. We start with this image collection for GDDP data, filter by dates from 2020 to 2100, filter it for a specific model GIS E21G, and filter for one scenario SSP 245. Here we are checking our data set, and so when you print something, it appears on this console window. And so this is print dataset, and this is dataset first 90 elements are printed here. So this is the collection. If you look at the bands, all 9 parameters are available, and when you go to properties, this is the model name, this is the scenario, and this is 2020 day 1, and it's for first 90 days. It shows that the data set that you have picked, it's kind of confirming that the data we picked here are the one stored in data set. Next, in this block, now we are getting just one parameter out of those 9 parameters, and we'll start with defining a variable air T. This collects surface air temperature, daily temperature, and this is daily mean temperature TAS. So we start with that. So this is global air temperature TAS, we further clip to my AOI. So this is ART regional. Now we take our global ART collection and clip it to our area of interest. In this case, it's Nebraska. Now, as we saw earlier, temperature data are in units of Kelvin, and to convert it to Celsius, we have to subtract this number 273.15 from the Kelvin temperature, and that's what is done here. So at the end of this operation, ART underscore regional temperature will be available in Celsius because we are subtracting this constant. Again, this is printing for checking our data, and you can perhaps confirm that by looking at image collection and features and look at the elements. So here now you will see that you will have just surface air temperature, not all 9 parameters, and same image properties are there. So this is the data set we will be using to calculate annual mean and then time series. So first we will make maps or annual mean maps for 2020, 2050 and 2100. This entire block does that. It starts with year, start date and end date. So it's starting from 2021 first day to last day. Defines an image collection TYY. And so that just has 1 year worth of daily data, and then T2020, that's the annual mean temperature that takes this TYY image collection and uses this reducer mean to get annual mean for T20. This is again just printing and checking down here. You can click and see what it shows. After doing this for 2020, it's exactly the same procedure for 2050 and then again for 2100. So at the end of this section, we have 3 maps: annual mean 2020 surface air temperature, 2050 and 2100 surface air temperature. Next, we take differences of these different temperatures. And here we define 2 variables shown here. TDIF, this is 2050 minus 2020, and this is 2100 minus 2020. And that's exactly what it's doing, taking annual mean and subtracting T2050, T2020, T2100, all calculated in previous segment. And so at the end we have temperature differences. Now we are actually mapping or visualizing maps. So we are defining visualization parameters. For air temperature, we fix minimum to 5 and maximum to 15 degrees Celsius and assign color table here. And for temperature differences, our minimum and maximum values are minus 0.5 to 4 degrees Celsius, and again colors are assigned for maps. And these 5 statements, map dot add layer, actually plots map on this map panel, 3 years annual mean temperature, and then the 2 differences, and we will inspect them at the end of this script. Next segment does the same for precipitation. We have precipitation maps for 2020, 50 and 2100. Only thing that changes is that our data collection now is PR instead of ART. Now we have precipitation data set and it selects PR. Then it defines PR underscore ridge and it clips to my AOI, my area of interest in Nebraska. And again, this is printing. And here there is one more constant. What that does is converts millimeter per second precipitation to millimeter per day. So it multiplies precipitation values by 3600 seconds per hour, 24 hours per day. So when you multiply by this constant to precipitation values, you get data in millimeters per day. Once we have that in this block, we start with 2020. this is again PRYY is the image collection for 2020, day 1 to last day. And then this is just finding annual means. So from daily data, now we have annual mean data for 2020. Similarly, we have the same for 2050 and for 2100. Then we also check differences between precipitation. So we define PRDIF here, precipitation difference, 2050 minus 2020 and 2100 minus 2020 by subtracting this annual mean data. This is very analogous to what we did for temperature. And here we define visualization parameters, 0.5 to 3 millimeters per day for precipitation, and for differences it's minus 1.5 to 1 millimeters per day. And we add layer, map.add layer, so add map to the map window, 3 mean precipitation data and then 2 differences. Next, we will make time series of surface air temperature and precipitation for this 81-year period, 2020 to 2100. For both temperature and precipitation, calculation steps are the same. We first start from the data collection or image collection, calculate annual mean. So we have first we have 81 maps, and then for each map we find area average quantity for 81 years. So for each year we have number averaged over Nebraska, or my AOI here. Then we plot that time series, fit a trend line and plot that too. In this segment, the year list is formed. So starting from 2020, increase by 1 year to total 81 years. And then from filter collection, which is daily data, from that annual mean data are found. So T annual from this image collection. And here we have used original image collection, which was in Kelvin. So again, we are converting data to Celsius. So at the end of this segment, we have T annual image collection, which has annual mean for 81 years. So we have 81 maps here. Now we are plotting time series by using this ui.chart.image.series by region command here. We define a variable time series, image collection is T annual is used, and so each image now is averaged, found mean over my AOI. The scale for this data is 25,000 meters because the resolution of the data is 25 kilometer. So based on that, this mean over my AOI is found. And then the property here is, this is the administrative region name. You can have multiple shape files. You can define multiple administrative levels for which you want to do this analysis. That's why we are identifying this with this particular administrative name. This is for visualization. This is the title of the time series, vertical and horizontal axes, titles, and their values are given. So max and mean are 8 and 15 degrees Celsius. And then we are labeling it as T air. Once that is done, part of that, there is a trend line fit to that time series, and then that is also part of this time series, both annual mean and then the fitted line as well. Here, this time series variable now is set to chart type line chart, so we can plot lines. And when you say print time series, that time series is plotted on the console window here that we will see. This was for temperature. Exactly the same steps are followed for precipitation, making annual image collection, then converting it to millimeter per day, and here for each year now precipitation is averaged over my AOI, and trend line it fitted there, and then it's plotted. So PR time series also is printed on the console. So when you go through this script and you run the script, you will see results. So let's first of all look at time series. This is annual mean surface air temperature for Nebraska, and this is linear trend. And you can see for 81 years, this is in Celsius, you have increasing temperature trend in surface air temperature. So you can see the slope and intercept shown here. You can point to any of this and you will see the number for that particular year. You can also see that there is variability around this trend line. So interannual variability is there as well in temperature. If you look at the precipitation, you can see that there is interannual variability. Initially there is more rain, slowly there is decrease in precipitation over Nebraska over this year. So clearly both surface air temperature is getting warmer slightly, and precipitation, annual mean precipitation is decreasing overall. Both have interannual variability. Next, let's look at the maps that we plotted for different years and temperature differences and precipitation differences as well. So here all the layers you can choose to plot here and to make them visible. This is just the shapefile for Nebraska. Let's start with air temperature 2020 in Celsius. If you click on this wheel here, it shows the range. If you go to custom and stretch to 100%, it shows exact range, and then it distributes with this color palette. So range here is about 8.2 to 13.1, and you can see that temperatures are colder in northern part, and as you go to southeast they are getting warmer. If you look at 2050, slightly warmer temperature there, and if you look at 2100, almost everywhere there is slight increase in temperature. And now let's look at difference between 2100 and 2020 surface air temperature. What you see here is that there's much larger differences in the northern part, northeast part, and there are less differences in the southeast part. So this is the spatial pattern we get in differences. If you look at precipitation for 2020, and values are shown here, about 1.3 to 3.3 millimeter per day. Much larger rainfall in the eastern part, and it decreases. There's a gradient as you go towards western part. If you take 2050 and 2100, now you see that there is a decrease in precipitation over western part. And if you look at the differences, and let's look at the numbers here, it's minus 1.15 to about 0. That's the difference. Here it's negative, so that means more decrease in rainfall in this part. And if you compare this with the temperature difference here, you will see that in this part you have warming going on and decreasing precipitation going on in the northeastern part of the state. So you can see the spatial pattern also. This is again from one model, GIS. You can explore this from other models and compare. Ideally for your own region, you would pick the model that is closest to observations in your area and then follow that model. Or you can take ensemble mean, you can take multiple models and take average precipitation and temperature and do the same analysis. It's computationally takes more time, so that's why we right now are focusing on just one model, but all these possibilities are there. So this concludes our precipitation and temperature analysis, and now what we're going to do is look at the extremes. Next, we are going to examine how extremely cold event frequencies are changing between 2020 and 2100. And for that, we are focusing on winter season and daily minimum temperatures. Now, this script for cold events is also available to you through training webpage, and you can follow along. The first part of the script is pretty much the same. All the definitions are the same as we saw in the previous script. So we will not be going through that in detail, but just main analysis is what we are going to focus on. So these are the databases that we used before for country and state level. We are going to use the same image collection, NASA GDDP-CMIP6. We are going to pick GIS, NASA model GIS for analysis, and SSP 245 scenario for analysis. Here we are going to select daily minimum surface air temperature. First, we are going to collect daily data for 2020 to 2100, and from that we are going to form seasonal image collection for December, January, February of each year. We're going to clip the data to our region of interest. Again, we're going to focus on Nebraska, and then we are going to look at extremely cold events. So first, based on the seasonal time series of images between 2020 to 2100, we will calculate 10th percentile value of daily minimum temperatures. Then we'll compare each daily image of minimum temperature with this 10th percentile value, and if the daily minimum temperature is colder than the 10th percentile value, then it will be considered extremely cold event. So 10th percentile value of temperature is used as a threshold, and that is how we count extreme cold frequency. So we do that by for each year for winter season. This section is just definitions of variables, and we'll start with the analysis. This section selects region of interest, and it adds to the map below, just like we did in the previous script. And now we will start with the analysis, main part of the analysis. Here is our data set variable, which filters our original image collection with dates, with model, and with scenario. And print statement, as in previous script, is just writes on this console window, and we can check the data. Next, we define ART. From dataset image collection, it selects daily minimum temperature TAS mean and assigns it to ART. This is still global image collection for daily minimum temperature. In ART_ridge, now we clip it to my AOI, Nebraska, and so we have regionally clipped ART_ridge image collection of daily minimum temperatures. Here we define start year and end year. Here years are listed from start to end year. And this entire block here, it forms image collection in such a way that for each year, daily images from December, January, February, or winter season are stored, and they're tagged by each year. Variable DJF image list stores the list of processed images. It iterates over each year and populates this image list. Note that for winter season, December of previous year is considered, and January and February of current year are considered. So that is taken care of by this dot subtract here from year. So for winter season of say 2025, December from 24 and January, February from 25 will be considered. Also, it checks for leap year. If it is a leap year, then last day of February is considered 29th. Otherwise, it is 28 days. And so at the end of this segment, we have season images, which holds daily images for each winter season for DJF per year, and they are listed here. Furthermore, this list now is converted to DJF collection or image collection. So this is the final DJF collection, which holds image collection for winter season for each year, and that is used to calculate 10th percentile value of temperature as shown in this segment. We define a variable T10 perc that uses DJF collection and uses dot reducer dot percentile 10th percentile to get 10th percentile value in this variable. Also note that in GEE, percentile values are stored in a default band. So it would be TAS mean underscore P10 in this case. If it were 20 percentile value, it would be P20. If it were any other variable, that variable name would be here. So further, this T10 perc is in Kelvin. We are converting it to Celsius like we did in the previous script by subtracting 273.15. So we have T10 perc C in Celsius. So this is the variable that holds 10th percentile temperature value in Celsius based on this entire time series. So now we calculate frequency of extreme cold days. We define variable T10, which holds band values of TAS mean underscore P10 so that is the 10th percentile value for temperature, minimum daily temperature. Then we have a variable seasonal cold counts that is applied to each year, and it's the result of this calculation here. So what it does is for each year, first of all, defines a season images variable in which just 1 year of winter season images are held, and they are filtered from DJF collection, which is all the DJF images for all the years. So per year, season images are stored. So these are daily images for 1 year for one winter season, and for each image, grid point by grid point comparison is done with T10 value. And so if for any day at any grid point, if daily minimum temperature is less than 10th percentile value of temperature, then it is assigned extreme cold event value and it is set to 1. Otherwise, it is set to 0. So we have binary images collection that is arrays of 1 and 0 for each day in a season. And so then cold count is just sum over entire season. It counts ones and zeros for daily binary images in one winter season and comes up with cold count, which is for that particular year, that season has this cold count, which is the cold number of days, and that is returned back to this variable. At the end of this block of code, we have variable seasonal cold counts that is converted to image collection cold frequency. And what cold frequency image collection has is maps for each year from 2020 to 2100. For each year, each winter season, what was the frequency of extremely cold days that is stored in here. And for example, we are plotting one map for 2020. It shows map of extremely cold days over Nebraska for 2020, and this will be added to our map panel that we will view in a few minutes. Next, now we make time series of extreme cold events for my AOI or Nebraska in this case. So here variable time series is defined, and as we did in the previous script for average temperature and precipitation, here also we are using UI chart image series by region. Image collection is cold frequency for each winter season per year. We are averaging over my AOI. This is the resolution of GDDP data, 25 kilometer or 25,000 meters. And then these are annotation for plots for vertical and horizontal axis and title. We also fit a trend line and we plot that also. Here we define time series to set chart type to line chart, and when we print time series, we find that this time series is plotted in the console window, and we can expand this. So here is the cold frequency between 2020 to 2100 for winter seasons. So we have used minimum daily surface air temperature to find this. What is striking here is that there is very strong interannual variability. Extreme frequency, cold frequency varies from 2 days to about 19 days, and there is a decreasing trend in the sense that number of overall days are decreasing between 2020 to 2100. So cold frequency days are decreasing. There are less numbers of days which are extremely cold, colder than 10th percentile value. But you can see that there are very many years where frequency is very high. Many days have 15 days or so. So out of 90-day season, 15 to 19 days can be extremely cold. That's what this is showing. And if we look at the maps, this is the 10th percentile value of minimum surface air temperature. This is somewhat consistent with what we saw in climatological mean temperatures. The northern part temperatures are much colder than in the southern and southeastern part. Here we see that 10th percentile values are much lower in northern part, and they are higher somewhat in southern part. So there is a clear pattern here. If we look at cold day count, this is just for 2020. The values we checked, they vary between 2 to 12 days. Number of extremely cold days are less in eastern part here, north and eastern part, and they are somewhat higher. There is a pattern here. You can see here there is medium, there is low, and then somewhat higher extreme cold days are seen here. This is just for 1 year, but this is just an example. So this allows you to check extremely cold frequencies. Next, we are going to look at extremely hot days in summer in Nebraska. After examining the extreme cold event frequency in Nebraska during 2020 to 2100, next we are going to examine how extremely hot event frequencies they evolve during 2020 to 2100 over the same region. So the logic here is the same. We are looking at extremes. In last script we looked at extreme cold events. here we are looking at extremely hot events. So by now you know the flow and logic of this script, so I'm not going to go through every block because most of this is the same. I'm going to focus on what is different here in this hot event detection script. By the way, this script is also available to you for your use. You can follow along if you like. Now in here we are picking summer season daily maximum surface air temperature to detect very hot, extremely hot events. So we pick June, July and August months, and we consider daily maximum surface air temperature instead of looking at average or daily minimum surface temperature that we have looked before. So we for looking at the extreme hot temperature, we calculate 90th percentile value of daily maximum temperature for summer, and that is June, July and August, considering the entire period of 2020 to 2100. And then compare each daily image of maximum temperature with the 90th percentile value, use that as a threshold, and count as extreme hot event when the maximum daily temperature is warmer than the 90th percentile temperature value. So that is the flow here, and pretty much it follows the same path as we did for extreme cold events, but now we are looking at summer season 90th percentile, and we are looking at daily maximum temperature, not minimum or average. This is the same part. We load our area of interest. We start with the data set image collection here from GDDP with the same model and SSP scenario. We go down, and here now we define air temperature and extract TAS max. This is the surface air temperature, maximum surface temperature daily from dataset, and this is still global data. Now we clip it with our region of interest to get regional temperature, and define our start year and end year. And here now we are collecting JJA image list. You can see that this block it creates image list for all daily images for summer seasons for every year, and for that we consider starting date as 1st June and end date as 31st of August. So for each season, for each year, June, July and August daily images are stored in season images, and by the end of this block we have JJA image list variable containing all the daily images for June, July, August for each year, and we convert that to image collection JJA collection, which we use to calculate 90 percentile value. Here we define T90% variable and use JJA collection to find 90 percentile value. We convert T90 perc, this variable which is in Kelvin, so convert that to Celsius just like we did for previous script. And so now we have T90 perc C, this is in Celsius, and this is the one that we are going to visualize here. Now we calculate frequency of extreme hot days. The logic here is very similar to what we did for extreme cold days, but now we are comparing the threshold of temperature 90th percentile, and so that is the difference here, and we are using June, July and August maximum daily temperature for that comparison. So T90 holds threshold that is 90th percentile value of daily maximum air temperature from this band, and then we define a variable seasonal hot counts. This loops over each year. For each year all the JJA daily images are collected, and from this large image collection, and then extremely hot days and not extremely hot days are decided based on the threshold. So this binary image collection is working for each year. It compares daily surface maximum air temperature with value in T90, that's the percentile value. Comparison is done at grid point by grid point basis, and so we have image collection here for each day with 1 and 0 detecting whether it's extremely hot day or not. Finally, this hot count sums for each season, and it holds number of hot event frequency for that particular season. At the end of this loop, for each year between 2020 and 2100, we have seasonal hot counts for each summer season, and that is converted to image collection hot frequency, and that is plotted here for first 2020 as an example. So here hot frequency has 81 in the image collection for each year, and we are just plotting the first one here and adding to the map. Then we go on to make time series from hot frequency image collection. We use the same procedure as we did earlier to make time series. Here we start with the image collection average over Nebraska here, and this is the scale of the GDDP grid resolution, that is 25,000 meters. We annotate our plot. We fit a trend line to this time series, and we plot that as well. We further define time series as set chart type to line chart, and then print time series, which then is displayed here on the console window. So we see this time series here. If you look at this frequency for year, days with warmer than 90th percentile value, frequency varies from almost 0 to here almost 28-29 days. So here you can see clear increase in frequency of extreme hot days, and also see interannual variability. There are years with extremely high frequency of extreme hot days, 25 to 30, and there are many days between 15 and 20 which are extremely hot. So considering 90-day season, here you have 1/3 of the season with extremely hot days, and 1/4 or 1/5 here. So between 2020 and 2100, you see clear increase in frequency of extremely hot days. You can also view maps in this panel. You will have two layers. 90th percentile value of maximum surface air temperature, that is shown here. You can see that the value, 90th percentile value, is much higher in the southern part of the state and western part, and it is lower in this part, in the northern part. You can also look at hot day count for June, July, August 2020. This concludes our demonstration of these three scripts, one with annual precipitation and temperature time series, one with extreme cold event frequencies, and second one, current one, which is extreme hot event frequencies. We looked at those, and so we're going to stop this demonstration now. And what you can do is, whatever time you have, you can work on this fourth script, which is exercise for wet and dry event statistics, and it has the same logic. Now we are looking at precipitation data from dataset. It's named PR. So we are using PR and using the same logic that we find 10 percentile value of precipitation and 90th percentile value of precipitation. Then we go through each image for each year in summer season, June, July, August. And whenever we have precipitation that's less than 10 percentile, that is considered dry event. And if it is more than 90 percentile value, then it is considered wet event. And we have time series for those. So this is for higher than 90 percentile, this is lower than 10 percentile. So when you run this script, you should get these time series, and you will also see corresponding maps for 90th and 10th percentile value here. So what we're going to do is you have some time, you can copy this script on your own Google Earth Engine account and try to run this script. So you can work on the exercise using this extreme dry and wet events during summer season link. And this will be a part of your homework. You will be submitting these time series as a part of your homework. Looking ahead to part 2, we will have several demonstrations. We will learn to visualize maps of weather statistics for a region of interest using NEX-GDDP dashboard. Then, using Python Jupyter Notebook code for GDDP data access, we will learn to customize spatial and temporal selection of GDDP data, calculate frequency and intensity of extreme hot, cold, dry, wet events for a region of interest, and then assess changes in the extreme event statistics over the 21st century for a region of interest. So we are going to do this using Python and Jupyter Notebook, something that we did today using GEE. Here, however, you will be using some different indices to look at statistics. There will be one homework posted on 17th of September, that is next week after part 2. And that will, you can access that from training webpage. You will submit answers using Google form, but also you will be provided information how to submit your figures as part of your homework. Homework will be due on 17th of October. A certificate of completion will be awarded to those who attend all live webinars and complete the homework assignment by the deadline. You will receive a certificate via email approximately 2 months after completion of the course. Once again, we thank Dr. Bridget Thrasher for her excellent presentation and her help with this training. Here's the contact information for Dr. Thrasher. You can always contact us. My colleague Sean McCartney and myself from ARSET will be happy to answer any of your questions. You can visit ARSET website, and this is our YouTube link where all the training material recordings will be available. So thank you for attending today's session. Thanks again for attending today's session, and I hope that you can copy the GEE script and work on the dry and wet event calculations. We are going to go to the question and answer session. In the meantime, you will have the link for this script, so please go ahead and copy and try to run it. You have a month to complete this. It will be part of your homework. We will start with the question and answer session. Question 1 is, I want to know about the climate resilience in urban areas from the urban heat island. What are the climate models that I can apply to? Yeah, go ahead. Vijay, please.
Thanks. Sure. Any of the climate models could be applicable. I believe the GCMs that start or whose output is already at a slightly higher horizontal resolution are going to capture that. Obviously, the ones that are at, say 2 meters long sadly, the GCMs are not all on the same, they don't output their results on the same horizontal grid. So you would have to do some research to find out which ones are, as I said, that are at a, whose native resolution is already on the higher side. And those are going to, again, they should do a better job at capturing that effect.
Next question is, what is the resolution of original data that NEX is downscaling?
Yeah, this follows on to the previous question. They're all, as I said, they're all different. It could be anywhere from, say, approximately 3/4 degree resolution to as much as 2, maybe slightly more than 2 degrees. So it's highly variable, anywhere from 100 kilometers up to 250 kilometers per cell. So, yes.
Question 3 is, do you think it would be safe to use the NEX-GDDP-CMIP6 projections for future downscaling to 1 kilometer in one's area of interest using the BCSD methodology? Historical reference would be different.
Yeah, that's not a problem. I don't see any problem with that. If you're, I will just put in a plug for a different product. If your region is actually over the US, over CONUS, the lower 48 states, we have a different NEX product called BCP30, which is just over the lower 48. It's at an 800-meter resolution. So that's where you're looking. If your region of interest is in the lower 48, then I can point you to that data set, and then I will have already done the work for you.
Great. Question 4, for bias corrections, how did you manage to get observation data for every where over the globe?
Yeah, that's the reference data set that was used is actually a global product, the GMFD. There are several it's called a reanalysis, and there are several reanalysis products out there. That's just the one that I happen to use. And these reanalyses use a model to basically fill in all the gaps from the disparate locations of various observational inputs. So that's how they can make a global product.
Question 5, how is this data going to complement other NWP and reanalysis datasets, including the data from ECMWF? ECMWF has much more granular resolution.
Yeah, to my knowledge, ECMWF is it's weather forecasting. It's medium range. I think it goes out 3, maybe 6 months into the future. So this is obviously GDDP covers that time period, but also goes out to end of century, and it involves 36 models.
Yeah.
Yeah.
Yeah, so that's not, it's not a comparison because you're talking about many climate models and their projections in future, and ECMWF is purely a weather forecasting model here. So
Correct.
Is there a Python version available for this code?
No, there's not. I do have a colleague that approached me about possibly creating one, but I haven't gotten around to making that switch. The code is all in NCL and car command language, which has served me well over many years. So that's just what I've kept with so far. Yeah.
Right. So for data access, though, there are Python programs, and then next week we'll see that. Question 7 is,
Yeah,
thank you.
to access the archive.
Sorry.
That's okay.
Thank you for the workshop. I'm interested in when GDDP-CMIP6 version 2 will be released.
It's already out there, at least on NCCS. The version 2 files are available there. Amazon and Google Earth Engine, I honestly don't know if they've been pushed out yet. They have their own schedules for making their updates on their side, but they are currently available through NCCS, yes.
Great, thank you. Question 8 is, I'm working at the watershed level. So is it generally better to use regional climate model data for global climate model data or for such studies? Additionally, in this context, which downscaling method, dynamic or statistical, would be more appropriate and reliable?
They are, your question is somewhat context dependent. As far as applicable and reliable, they all have their, pros and cons, pluses and minuses, and they all do some things better than others. So I can't really answer that question as much as I want to say mine are the best. It could well be that that's not the case in your particular watershed. Yeah, I'm sorry, did I answer the full question? I lost track.
Yeah, I think it's fine. Question 9 is there some guidance document or best practice article for the way on how many and which models to select in building an ensemble time series for a particular region or adaptation application?
I would say to be sure to check the scientific literature to see what evaluations have already been done in your region with the CMIP6 models themselves. There's a whole body of literature out there that has explored these questions already. Yeah, so that's where I would start.
Right. Question 10 is on further BCSD downscaling. Would it be okay to filter out or narrow set of model projection? Is there a rule of thumb for narrowing?
For choosing the projections?
Yeah, it looks like a set of model projections for ensemble.
Yeah, basically what I've just stated to evaluate the models themselves for your area, which has likely already been done to some extent, and is likely available in the scientific literature right now.
Great. So
as far as which, sorry. As far as which like SSP to choose, if that's sort of what you're asking about, it's really, again, it's kind of application dependent and would be dependent on what question you're trying to answer with the data. If your tolerance is for your application is, if you have a large risk tolerance, or then maybe looking at the 25th, 50th, and 75th percentile is perfectly acceptable. If you don't have a lot of tolerance for risk, maybe you need to look at the 10th and 90th percentiles. It really just depends on what question you're trying to answer.
Thank you. If we have a few more minutes, if you have any additional questions, you can add to that chat box. Also, we have a few minutes, so if you want to go ahead and start running the script, that would also be possible on the Google Earth Engine. Our next session will be at the same time next week on 17th. But we want to thank you for attending today's session. We also want to thank Dr. Bridget Thrasher one more time for her time and her presentation and answering all the questions. Also our ARSET team, Sean McCartney, Selvin Hudson-Odoi, Sarah Carshell, Brock Blevins, Jonathan O'Brien, Sue Monty, Natasha Johnson-Griffin. We want to thank the team for helping with this training and coordination.
Oh, yeah, by the way, the version 2.0 of NEX-GDDP-CMIP6 files are available from Amazon Web Service, and will provide
great.
examples to use the latest version of NEX-GDDP-CMIP6 next week.
Oh, that's great. Thank you.
Thanks, Kyo. I haven't looked recently, so I'm glad you were able to follow up on that.
Mm-hmm.
Great. Thank you, Kyo. There are no more questions. Thank you for attending today's session. We hope to see you next week.